Okay, this is a result of a joint work with George Haller at ETH, Josefina Olascuaga at Rasmus, the same place where I am, our former student, young one, who's at UCLA now, Joaquin Trinanes from NOAA, who's been providing us with satellite data, and Paula Perez from CICESE in Mexico, who's been analyzing Lagrangian data that we're going to be using in this talk. This research is funded by the BP through the Gulf of Mexico Research Initiative, and also by Pemex through a similar initiative in Mexico. And these two projects are meant to focus on the transport of hydrocarbons in the Gulf of Mexico, and that's why I'm going to be focusing on the Gulf of Mexico. What I'm going to show in here is the evolution of a tracer under the advection of a certain incompressible two-dimensional velocity field. Just take that, then I'm going to be more specific about what type of velocity field I'm using. So if you look at the evolution of this curve, you put tracers in there, see that this thing stretches, takes highly complicated patterns, but in the center of the Gulf, there is this region which is not filled by tracer particles. This suggests the presence of some structure, a vortex, a Lagrangian vortex, with a boundary that cannot be penetrated by tracers. The point of the talk is try to get to this vortex, the boundary of this vortex, using this technique that we have developed. You may be thinking that why we do that once the already the topology of the streamlines of a velocity field is telling you that there is a vortex there. What I'm plotting in gray there is instantaneous snapshots of the stream function. Okay, it might work in this case, but in general, it doesn't work because of the frame dependence nature of the velocity field. And what I'm putting here is just one snapshot of a streamline of a two-dimensional velocity field, which is an exact solution of the Navier-Stokes equation. And in red, I'm painting this area. I'm going to evolve this patch under the velocity field, and at the same time, I'm going to be plotting the streamlines. And you see that they don't follow the evolution of a tracer, right? And why is that? The reason for that is because this thing, while instantaneously look like that, and we go and run any of these descriptors or Lagrangian descriptors of vortices. For instance, in this region, vorticity dominates over strain all the time and everywhere. But if you look at this on a certain frame, you will see that this thing is actually a hyperbolic region, a saddle point. So that's why we have this thing stretching along the unstable manifold. All right, so in the end, what we're going to be able to do applying our technologies is to extract this boundary. Okay, so I'm going to try to show you how we do this. So we do it in a way that is independent of the observer. And to do that, okay, well, it's a result of several papers. So when I'm focusing on one paper that we published with George Haller that appeared in JFM, and the paper that is ready to be submitted with these people, we have independent observations that show that these things are not artifacts of the velocity fields that we use. Okay, so we're going to need an objective description of the deformation, of interior deformation. We're going to start with a velocity field, which is incompressible, two-dimensional, and the particles evolve according to this finite time dynamical system. It's not autonomous because it depends on time. Finite time because velocity field is finite over finite time. Okay, we're going to have a flow map that relates the time t0 and time t positions of fluid particles. This is going to be smooth and invertible, provided that this thing is sufficiently smooth. And then we're going to introduce a concept of a material line. This is a curve gamma t, which is just the advection under the flow map of a curve formed by initial particle positions. A time slice of a codimension 1 surface in this extended phase space by time. be interested in special material curves, we have that property, that elasticity that that show this curve in the movie that I just showed. Okay, how we get to those curves? We introduce the concept of local stretching. So we have to introduce a parameterization for the curve at time t0. This evolves under the flow map into a curve gamma t. So tangent to a point at gamma 0 is the derivative is this vector, is tangent to it. At time t is the derivative of the image under the flow map of this vector, which is the differential of this thing, of the flow map times r prime. Okay, stretching is defined as the relative stretching as the length of this vector field tangent, this vector tangent to the curve relative to its initial length. All right, in here we have a gradient of the flow map, and you have the Cauchy-Green tensor, the right Cauchy-Green tensor, which is this thing transposed times itself. Okay, this is objective in the sense that it's independent of the frame adopted by the observer to describe this, because both df and f are objective through a change of frame characterized by this expression here, but this is a time-dependent rotation. The idea is that these two tensors map objective vectors into objective vectors. So an objective vector is one such that any observer would see the vector with the same size, but oriented differently. And in order for that to happen, this should follow under this transformation, the standard rule of vector transformations. And tensor should follow the standard rule of tensor transformation. This Q, this matrix, the tensor, Q transpose. And these two things change under that. So we have a frame-independent description of stretching of a material curve. This tensor is symmetric and positive definite, because of this, we have the eigenvalues are positive, and the eigenvectors are orthogonal. Lambda 1 is the smallest eigenvalue, lambda 2 is the largest, and they are inversely related because of incompressibility. The product of lambda 1 and lambda 2 has to be 1 because of incompressibility. One thing is this viewed as a field in the space of initial positions x naught. These things do not have a global orientation because they don't have intrinsic sign or magnitude. So, but the curves which are tangent to vector fields are well defined. And these in the visualization community are called tensor lines. So we don't talk about a vector field, but we talk about line fields. These are all the elements that I needed to post what we want to do. So we have a curve, material curve, and we put that on a two-dimensional turbulent flow. It's going to stretch typically and deform. But you're looking for things that, if start X-shape, will remain X-shape under the flow map. And how we do that? Well, we thought that maybe we should look at belts of fluid such that within this belt, the stretching average along the curves do not change to leading order. We can put that mathematically in a formal way, and this is what we have here. We have a functional, which is the loop integral of this local stretching, explained by this expression here, and the idea is looking for this belt is to take loops which are within the thin annular neighborhoods of the reference loop, and require that the total variation of this is doesn't change to leading order. Okay, this is equivalent to stating that the functional, this action, is stationary under these variations. So what we have in here is just the Euler-Lagrange equation. All right, this in principle will be solved. But it's a second-order differential equation, and it doesn't actually add too much clarity to the problem. We are up. We want to see what the shape of the R of S is. Okay, but we can exploit one property of these things. If you see the Lagrangian doesn't depend on S, which is the parameter of the time variable. And so we can use Nether theorem and show that the Hamiltonian, which is actually equal to the Lagrangian, is constant. So you see that the local stretching is constant. It means that each subset of the solution curves stretch by the same amount over a curve. So we have uniform stretching. So the expectation of this thing defies the exponential stretching that is typical in turbulence. All right, to get to those curves, we can in principle solve this thing. But this is an implicit, although it's a first order differential equation, it's implicit. But we can get an explicit one if you write R prime as a linear combination of the eigenvectors of the Cauchy-Green tensor. This is what we do this. We do this plotting here. We take this thing to have a unit norm, and we get this expression here, which is a first order differential equation, explicit, well, provided that this quantity is constant, is bounded, the square of the constant bounded from above and below by the largest and the smallest eigenvalue. Okay, solutions to this line field do not need to be loops, but closed curves follow as limit cycles of this line field. It's interesting that we started with a Hamiltonian vector field, and the curves of interest are to be limit cycles of a dissipative system. Okay, in a similar manner as in vector fields on the plane, where closed curves or closed orbits must encircle at least one critical point of a vector field, where the vector field is equal to 0, these things, limit cycles or closed orbits, must enclose singularities of the Cauchy-Green tensor, which is where the eigenvalues are equal. Lambda 1 is equal to lambda 2. And in this case, because of incompressibility, it has to be equal to 1. All right. Daniel Karash, was a student of George Haller, proved that actually you have to have two such singularities. And this turned out to be pretty useful when we go and try to detect these things, where we go and seek for limit cycles of the vector field. All right, we can be further show that these loops are non-intersecting families of loops because of this vector, this line field is a rotated line field. Okay, so what we have is we have a families of concentric lambda loops, and we take the outermost of this family as the boundary of what we call the coherent Lagrangian area. We may wonder why these uniformly stretching curves actually have this elasticity property that we've been looking at. Well, it turns out that from numerical experimentation, we see that these lambda loops tend to exist for lambda close to 1. And that means that the boundary, the length of the boundary is almost exactly reassumed at time t. Or you can see that by looking at the lambda equal 1 case. So you take the arc length of the image under the flow map of the initial closed loop, and you see that it's exactly equal to the arc length of the loop. All right, this arc length reassumption, together with the enclosed area conservation, which is as a consequence of the incompressibility of the flow, makes these vortices very coherent. So if we cannot, the curve cannot stretch and the area is conserved, so this, if it is egg-shaped, will remain near egg-shaped, just roughly. One interesting property too, when we're dealing with imperfect data, this is what we always do, is that because of these are limit cycles of this line field, these are robust under perturbation. So you expect these things to happen with under some inaccuracies of the velocity field. This is a consequence of the structural stability of limit cycles. Okay, briefly, how we get to this thing. So one has to integrate the trajectories given a velocity field we have to compute the flow map. That's what we're doing. By integrating trajectories, compute the gradient of the flow map, compute the using finite differentiation on a grid of initial conditions, the Cauchy-Green tensor from that, and the eigenvalues and eigenvectors. Construct this eta vector field and seek for limit cycles. We can identify regions. We have singularities of the Cauchy-Green tensor surrounded by regions where they're free of singularities, and this is where these things should exist. We have two possibilities, the plus and minus in that vector field. We see which one has limit cycles. To get the limit cycles, you just go and take a Poincare section, and you see, look for fixed points of the Poincare map constructed that way. And we take the outermost of this concentric family of lambda loops as a boundary of the vortex, the Lagrangian vortex. And this is what I'm plotting here. What I've just showed. This is the boundary of the vortex on top of the instantaneous streamlines. This followed from an integration of 200 days, and this vortex has lambda equal 1.05. So after 200 days, the length of the curve will stretch by this factor. This turned out to be the largest and the longest lived Lagrangian coherent vortex that we could extract from this velocity field. And plotted below the same thing, but the extraction, but from a frame that is rotating relative to the frame that is attached to the Earth. You see that you don't see the concentric structure of the streamlines, but if we go and apply our techniques on this velocity field, we still get the same structure. This is the frame independence that I was talking about. Okay, now a word about the velocity field. They said it was a two-dimensional incompressible flow, and it's actually an imperfect representation of the velocity field in the ocean. It's certain synthesis of actual observations given from satellite altimetry, which measures the deformation of the sea surface height. Through geostrophy or quasi-geostrophy can get a velocity field. So basically, eta, the sea surface height, is like a string function. These things are available since 1992. There are maps for these things, and the resolution is coarse. So there may be things that are not sampled by the altimetry. So there's always certain degree of skepticism about the relevance of these vortex structures that we extract from altimetry. And of course, there may be other motions that are not geostrophic that may be playing a role there. So what I'm trying to convince you now is that these things are actually significant. I'm going to be, unfortunately, you can see this well. Well, what I'm plotting here is this extraction on top of satellite derived chlorophyll. There is a patch of chlorophyll. You don't see anything. And blue is actually a region of low chlorophyll, and it comes from the Caribbean Sea, which has lower chlorophyll than the Gulf of Mexico. And it's nice to see here. You cannot see here. There is this loop current, and it occludes and forms this eddy. So it's a nice example of this conceptual idea of how vortices are formed from the as an occlusion of a current. They call those type of vortices rings. This is a coherent Lagrangian loop current ring. I can show you the animation because you don't see here what I'm trying to point out. It is a blue patch. So this is saying this is actually a Lagrangian vortex. And also, we have satellite track drifters. This is a pretty unique. I mean, you don't have these two independent observations available all the time. Chlorophyll, or like a almost passive tracer, and also these buoys that deploy in these regions. Okay, these tend to follow pretty well the structure, but it's, I mean, interesting to see is the smoothness of the trajectories. There are little wiggles there, but these are only, if you take doing a spectral analysis with it, you see that it's a peak in the inertial oscillation only. So there's no continuous, spectrum as when it would expect it from the presence of submesoscale motion. It's just the inertial oscillation. There are some that do not stay near of the vortex, but the reason for that may be explained by the finite size effects. These buoys actually are anchored at a certain depth, but the anchor sometimes is lost. It's a parachute type of drifter that you never know where it is open when they drop it from a plane, but some that go away may be explained by, we have a result for spherical balls that float on the ocean that should be repelled away by anticyclonic vortices. So those that do not follow the vortex so closely may be explained by those effects. Okay, why we care about these things? We care about these things because they can carry stuff around. In the event of an oil spill, this thing can be affecting this area, or because of they are bringing species, larvae of different regions, connecting regions. But they also can have some climatic effects. So we've been focusing for some time in this region of South Africa, the formation of Agulhas rings. And these have been identified many years as a mechanism for the exchange of water between the Indian Ocean and the Atlantic Ocean. The Indian Ocean is saltier than the Atlantic Ocean, so the fact that you're bringing salty water in here can have implications for the thermodynamical budget. Okay, but these things, you see, they can carry pretty effectively stuff from here to there and eventually take another path. Okay, how many are there? We have computed this using the whole data set of altimetry, and the first computation said that the transport by this may not be as important as we originally thought compared to estimates of the Agulhas leakage. But a new computation that we have made revealed that actually they may be more important as we originally thought, but still there is uncertainty about how much transport is being crossing this area here. And the way that is computed, we believe we need a Lagrangian approach to that, and there is one, so we're going to be working on that. So final comments on this. This coherent Lagrangian eddies or vortices, I personally use my own code, but there is a toolkit, the Lagrangian coherent structure toolkit available. If you search for this, you can find it. It was done by, I can't remember his first name, he was a student of George Haller. Things that I haven't been able to go through, but these lambda loops are actually geodesics, and we can see that by an appropriate reparameterization of the curves that make the Lagrangian quadratic. The metric is actually a Lorentzian, it vanishes. So these are null geodesics, and this has enabled a cosmological analogy that got some people irritated and some other people very enthusiastic about, to the extent that having even postulated that these vortices may be explaining the Bermuda Triangle. We don't claim that, but you may see that in the with the search in the internet. All right, lambda loops are special classes of Lagrangian coherent structures of elliptic type. These are generalized KM tori, and they indeed approximate very well KM tori in maps with very few iterations. I'm working with Rafael de la Llave in Georgia Tech. I'm trying to see if KM theory, and actually an adiabatic theory, can explain the occurrence of this CLE in the ocean. This is connected to the problem of the stability of vortices that is not solved. So maybe we can say something based on KM theory, but an adiabatic type of KM theory. Okay, a complete 3D picture can be obtained if you apply these technologies level-wise. This is most appropriate in mesoscale flows. Of course, you have to have a representation of the velocity field inside in the vertical column. A full 3D analysis is possible now using an objective vorticity-based approach. In 2 dimensions, it's similar to the geodesic eddy detection that I was talking about today. These vortices allow some filamentation, but the filamentation is only tangential. You don't have control on how much filamentation is possible there. And working processes is the characterization of swirling structures in dissipative velocity, like those that are evident in vorticity snapshots of some mesoscale permitting of resolving ocean models, or even the picture of the great red spot in Jupiter, or a hurricane. Those type of things we cannot frame using these techniques. So maybe something else is needed. We're working on that using probabilistic and a probabilistic approach. Okay, and that's all that I have to say. Thank you.
So we have time for a few questions.
Have you compared the vortices you identify with something like what Chelton does, looking at just the altimetry field and using Eulerian techniques?
Oh yeah. We've made yeah. Well, Chelton, he looks just at the velocity field, not even at the Okuo-Weiss diagnostic, and he identified many more coherent vortices than we identified. And if you go and take those and put traces in there, they filament pretty quickly.
Any other questions? Very good.
It's a vague idea, but if you look for vorticity forming closed contours, would they coincide with regions you identified using your criteria?
In this case, they may. The example that I just showed, when you have a vortex of this type, then that may be the case. But in general, that doesn't happen because vorticity is frame dependent. Vorticity deviation, that thing is not. If you subtract some special, we see this with regard to the mean of vorticity field. That is objective. These things are close to integral. That's and this is what game theory does. So they look for canonical transformation that make things constant eventually. And what I'm showing here, they have these closed contours of SSH, of string function, and the presence of this. Again, there's a whole foliation of these curves here. They're pretty close to these streamlines. But that tells that there is this frame in which stuff is constant. But you have to find this foliation first to conclude that. In general, you see these closed contours, and you can see it happens what I show in that second animation.
Can I ask a question very quickly, if I may? As you know, Ian Percival and Jim Meese and others developed a method, a variational method for calculating Cantor array in maps which are chaotic, which would really identify, as you know, possible neighboring solutions.
Okay.
Could you comment on the relationship between what you do here and the Percival-Meese construction for Cantor array?
Yeah. I'm not aware of the details of that, but those are for maps. And
Yes.
we deal with aperiodic flows. Aperiodic and defined on a finite time.
But you're still correlating your results to results with maps in any case, aren't you?
Well, that's an observation. Whether we can, well, if those techniques get to the tori, and we also get into the same tori but through this different approach. I'm not aware of the. I have read.
This is dynamical systems.
No, I know what you, but I don't remember the details now. But we cannot use that. They may be extended to aperiodic flows, but I believe it's just very strictly applicable to maps, and maps are periodic.
Thank you. Let's move on to the next speaker, Xiangyu Li from Nordita, an effect of combined turbulence and gravity on cloud droplet growth.
thank you very much for giving me this chance. I'm going to talk about the effect of combined turbulence and gravity on cloud droplets growth. This is one of my ongoing PhD project. So we know that the Earth is almost covered by 76% of the clouds. And the clouds is the factors that are controlling the distribution of the clouds, and the radiative characteristics is included in the most urgent scientific problems requiring attention in the evaluation of IPCC in 1996. And cloud is really important for radiative forcing, and of course for the energy budget of the Earth. And it is also very important to the climate change. And one of the most challenging problems in the climate model is cloud physics. So here it is also stressed that by understanding more about the physics of individual clouds, we can help refine weather and climate models. So the fundamental physics for the raindrops is a bottleneck problem. It states that we have existing cloud droplets. It first grows by condensation from about 2 micros to 20 micros by condensation process. And then when it grows larger than 20 micros, it will grow by collection driven by gravity or the proposed turbulence. And then we have a growth gap between about 50 micros to 40 micros, but neither this diffusion mechanism or the gravitational collision mechanism is effective. So what is the mechanism that proposed to solve these bottleneck problems? Is turbulent collision. As we know that in the clouds, we have the Reynolds number about 10 to 7, so it is really a very turbulent environment. And we have cloud scale motion, scale flow with the size about 1 kilometers to the dissipative eddies, but with the size 1 millimeters. And they from these individual clouds, because of the condensation, we will have latent heat release. So the latent heat energy is flowing from the small scale to large scale, but the turbulent kinetic energy is flowing from the large scales to small scales. And so the scales in clouds is really multiple. And also this condensation and the collision problems also very important to understanding the formation of the planet. As we know, we have dust grace with a size about 1 micrometers, and it grows through condensation and collision and other process to planetesimals with a size about 1 kilometers, and also accretion to become the planet. So it has a length scale separation about 10 to 13. And here we will mainly focus on the formation of the cloud droplets to understand the fundamental physics of the condensation and the collision driven by turbulence. So the main difference between the clear sky and the clouds is that the clouds will have liquid water. And so to characterize this liquid water content, we need to know the mean number density distribution of the cloud droplets as well as the size of the cloud droplets. So here, if we know the spatial distribution of each cloud droplets, then we can calculate this mean number density of the cloud droplets. And the mean number density of the cloud droplets is also important to understanding the entrainment. If you know this spatial and temporal distribution of the cloud droplets, you can know also the optical properties of the clouds. So the basic physical picture of the condensation process is that if you have existing cloud droplets, the water molecules will just condense on the cloud droplets as long as the environment becomes supersaturated. So here we have this water vapor flux towards the droplet, and to conserve the mass, the water vapor flux is constant. So here we obtain this condensational growth law. And if we assume that the supersaturation is constant, we will get the growth has a T2.5 growth law. And so from here we see that the growth rate of the cloud droplets by condensation is inversely proportional to the size of the droplets. But to form these falling red droplets, the cloud droplets has to grow from 2 microns to 1 millimeter. So we need another mechanism to drive the growth of the cloud droplets. So this is a collision. The basic idea that in the clouds, if you have droplets with different size, they will have different falling speed. They will just collide with each other and merge together and become larger cloud droplets. So, but the distribution of the cloud droplets is inhomogeneous in the clouds. And so if we know this number density distribution as well as this collision range, then we can count the number of collisions. So to obtain this number density distribution function, we just solve this Smolkowski equation. Here we have the source term, which means that 2 cloud droplets with size m and m prime, they just collide with each other. And with this certain size, they have a number density distribution function. And here we have a half because we don't want to count the collision twice. And here's the sink, because when 2 cloud droplets collide with each other, they will disappear and form a larger one. So here we have a sink term. So you see from here, the Smolkowski equation is basically a nonlinear equation, and so that's why we use direct numerical simulation to solve these collision problems in the turbulence. And here are some observational studies that the first one I showed, this airbow cloud turbulence observation system shows that the Taylor macroscale Reynolds number in the clouds is about 10 to 4, and which means that the turbulence is well developed in the clouds. And also in 2015, and Bills et al., they observed that the distribution of the cloud droplets is inhomogeneous in the warm clouds. And also there are other measurements in 2013 and also 2007 that they observed this inertial droplet clustering occurs in the turbulent clouds. And this is also confirmed by the laboratory experiment that they had the spatial clustering of the inertial particles in high Reynolds number turbulence. And so here in our numerical simulation, we just study the collision events in the local area. We just take a small box with the size about 0.5 meters, and then we drive the turbulence by random forcing and with periodic boundary conditions, so that we don't have any cloud droplets lost in our compute in our simulation. And so within the clouds, the URMS is about 1 meter per second, and with the viscosity of the air about 10 to minus 5. And from here, we can estimate that the Reynolds number in the atmosphere is about 10 to 7, but in our simulation, it is still much smaller than this real Reynolds number in the atmosphere. So our goal here is to try to solve these collision problems in the turbulence, and especially this combined collision and condensation problems to bridge this bottleneck problem, and then compare the results with observational data. And so the equations are all solved by Tensor Code, and it is public domain. You can find it here. So because this collision problems of the inertial particles in the turbulence is a strongly nonlinear problem. So we first developed this Euler scheme. This is basically Smolnikowski equation, and we just discretize, and then we solve these momentum equations in inertial particles, because the cloud droplets has a density about 1,000 times compared with the gas flow, and also the equation of the gas flow. This is Navier-Stokes equation with the viscous term, and also with this continuous equation. Here, because for Smolnikowski equation, we have particles with different size, so we are using mass spinning methods. The basic idea is that if we have cloud droplets with different size, we just put them into different bins. If they just collide with each other, they will grow, they will jump into these bins. So at forth. And because this nonlinear, so we're not sure if this Y scheme is good enough to simulate the problem. So we also developed this Lagrangian scheme to compare with this Euler scheme, so that we can become more confident of our simulation results. So the Lagrangian scheme, for this Lagrangian scheme, we just solve the trajectories of each individual particles, and then we just track the collisions and along these trajectories, and see the size of the cloud droplets at different time. But of course, the ideal solution is this directed Lagrangian tracking, because in this case, we can really track the collisions in a real space and real time. But if we want to track particles with a number of 10 to 8, and then with number density of also 10 to 8, then the maximum computation domain we can reach is about 1 meters. But in the clouds, the integral length scale is about 100 meters. So it's far away from the real atmosphere. So that's why here we use this modified Lagrangian scheme. It is called a swarm model, basically it's a multicolor methods that we just represent certain number of cloud droplets with one super particles. Then when we track this condition, the first concept that comes into our mind is the mean-free path. If we have two cloud droplets, they just collide with each other, we can calculate its mean-free path. And then the two cloud droplets will have velocity difference, then we can obtain this collision frequency. Once we have this collision frequency, then the probability of collision can be obtained through the ratio between numerical time step and this collision frequency. And then, so they will generate the random numbers from the computer and compare with this probability of collision. If it satisfies this condition, then we can count these events as a collision. And the collision conserves momentum during this process. So our methods can ensure that the collision is symmetric between superparticle I and superparticle J. So here's some experiments of the comparison between the two simulation methods. So here we use this Eulalia methods to simulate the collision, here we already simulate this supersaturation, but here we just assume that the supersaturation is constant. And with the constant supersaturation, we have a analytical solution of the number density distribution of the cloud droplets. So here we compared with the Eulalia scheme, this black curve, and also with this Lagrangian scheme, we see that this Lagrangian scheme can almost get the same solution as this analytical solution in this condensational growth. And even for collision process, we see good agreements of the size spectra between Eulalia model and Lagrangian model. So, but here we use about 1,281 mass beams to make the Eulalia approach convergent to Lagrangian approach. So, which means that the Eulalia approach is more expensive than the Lagrangian approach in this sense. So in the future, we will mostly focus on the Lagrangian approach. And here is some comparison in the two-dimensional turbulence. And from the size spectra, we see good agreements, and also for different moments. The different moments characterize the collision of the droplets of different size. So especially these high moments characterize the collision between larger particles. And we see from this mean radius that it is not a very good quantity to quantify the growth of the particles, because in the clouds we always have a wide distribution of the size spectra instead of the mean-sized particles. But this high moments has very good agreement between the swarm model and this Eulalia model. So here we conducted this collision process in three-dimensional turbulence with a Lagrangian approach. And here we can reach the Reynolds number about 690, and with the bugs about 0.5 meters. And this is a snapshot of the distribution of the cloud droplets after collision. This is like 1,000 seconds, and we can see from here that the distribution of the clouds is very inhomogeneous, and we see few large cloud droplets, and so within this computation domain, it has such range about 3 micrometers to 100 micrometers, which is already the size of the drizzles. And here we comes the results. We see that if you have both turbulence-driven collision and gravity-driven collision, the growth rate and also the collision between large particles is even faster than the one purely driven by gravity or by turbulence. So which means that when we start this collision process, we cannot only focus on one process like gravity or turbulence. We have to combine them together to see the growth of the cloud droplets. But it's the interesting thing that if we combine turbulence and gravity together, then we increase the Reynolds number. Then we won't see any enhancement effects. Instead, we see that if you increase Reynolds number from 266 to about 6,000, we see that the growth rate just decreases with increase in Reynolds number. So this is quite interesting because we may just intuitively think that if you have high Reynolds number, you have a higher collision rate. But from our simulation, we see that it is not the case because there is a competition between gravity and turbulence, and because for the collision, there are two mechanisms that will contribute most to the collision process. The first one is clustering, another one is acoustics. Because when you have clustering, the local number density of the cloud droplets will increase, and then the collision rate will increase. And when you have acoustics, which means that the velocity difference between two droplets will increase, and then the collision rate will also be increased. So from these two aspects, we would explore that how exactly does gravity affect this clustering and the acoustics and the turbulence. And if gravity and turbulence exist at the same time, how these two effects compete with each other. So this we haven't understood yet, and it is just in the process. And so here's a conclusion that we found in our simulation that the growth rate of cloud droplets decreases with increase in Reynolds number when we have both gravity and turbulence in the collision process. And also our simulation shows that this Lagrangian model agrees well with this analytical solution, the condensation, and so it's superior over the Eulerian model in terms of the computational performance. And so we hope that we can try to understand this mechanism of competition between turbulence and gravity. And especially in the future, we will also study this turbulence effect and the supersaturation, because now in our model we are only using this isotropic supersaturation, which is unphysical, and there we are planning to develop these results to the parameterization of the collision model in large eddy simulations. And that's all. Thank you very much.
Can you say a word about the numerical code you use for the DNS of the dispersed flow in the end?
Sorry again, what is...
What is the code you use to obtain this this last DNS that you presented?
pencil code.
Sorry, say again.
Pencil code.
A pencil code.
Pencil
Oh,
code.
okay.
Yes.
So you mentioned that there was lower growth at higher Reynolds numbers,
Yes.
and the Reynolds numbers that you're using are still, I think, a bit small for real systems. So is that a problem then? That you would think that maybe the growth rate is even smaller than what you're measuring in your simulations?
Yes, I think that's possible. But I mean, in the current simulation, we see that if you have an order of 1, we didn't see enhancement, or we just see this this decrease with the increase in Reynolds number. So we can we can even push to high Reynolds number to see the results. But I think if they have an order of 10, that we still cannot see enhancement or even that it will weaken the growth of the cloud droplets. So it may indicate that there is a competition between turbulence and gravity. Yes.
When two small droplets collide and form a larger one, expect the larger one to move at slower velocity. Does that affect in your model? Because larger droplets, which in general move more slowly than smaller ones?
I think if you have pure gravity, the larger ones should have larger terminal velocity, and it falls even faster, so it will accelerate this collision process instead. But for turbulence case, if
It'll go the other way. Right?
yes, yeah.
Yeah, I was not thinking about gravity. The other thing is that you're doing this in a periodic domain, right?
Yeah.
So droplets getting out are coming in through the other end. But in a real cloud, you'll have losses, convective losses of things that leave.
Yes,
That term
indeed.
is not there, so your growth rates are always going up, but won't they turn around? I mean, there should be some convective loss in the system, no?
Yes, I think in realistic clouds, indeed, they have this. But I mean, for now case, we have a very ideal simulation. So even in this case, actually the growth rate is not even enhanced by turbulence, which is always believed to be the case. So I think, yeah, but that's really good idea that in the future we can have this entrainment process included, as you suggested.
Axel?
I just want to clarify, it is of course important to include convection and also thermodynamic properties of the real flows. At the moment we are just at the beginning of trying to make contact with the better models. Regarding your question about the velocity term, there is in fact an additional term in the velocity equation for this Minkowski equation, which was not written down here and also not in our original manuscript, and that is what we have now included to therefore preserve momentum conservation in this Minkowski approach. In the other approach, it was always included.
Your collision kernels in your Smolakowski equation are the rates of merging versus breaking apart of droplets well constrained by experiments?
Exactly, because in our simulation we just use this perfect collision rate, which means that this collision efficiency is always 1. So the breakup or fragmentation or things like that were just omitted for now.
I would think as you increase the velocities, that would be an important consideration. Yeah.
If there are no more questions, this is time for a coffee break, and we'll resume at 10:50. Thank you. Oh, am I on?
Just so everyone's aware, we're going to meet outside for a group photo.
Oh, that's right. Thank you. I forgot about that. Yes.